So good afternoon, colleagues, students, and those friends who are online. Welcome to this afternoon's colloquium, Cosmology, a Golden Age. In the late 90s, and actually since then, the physics department used to host public lectures of this type for the campus community. Until we had really distinguished guests such as Professor Yin-Zhe Ma, Professor Samuel Ting, and Professor Yin-Zhe Ma, and Professor Stephen Chu, and Professor Paul Chu, and many other distinguished guests. So due to the COVID in the past few years, we have to stop these events, but I'm so happy that now we can see each other and meet the speaker on site again. So before I introduce the distinguished speaker, I'd like to invite the head of the department, physics department, Professor Yin-Zhe, to say a few words of welcome.
Good afternoon. Thank you for organizing this ICTS physics joint curriculum, and it's really exciting to have this face-to-face academic exchange again after this long time of program. Today we have this distinguished guest from far from South Africa, and we also learn to use the online platform. So we have the mixed mode to reach out broad audience. So I think after all these challenges, we are moving to a new era. And today the topic is again cosmology and golden area. I think not only cosmology or physics is facing a new area. Physics aims to understand our universe from the smallest scale of elementary particles to the largest scale of cosmology across billions of light years, right? And I think today Dr. Ma will show us that these two smallest and largest scale are strongly interlinked, and we humans are living in between in a complex world, but we are facing imperative challenges like climate change, energy problem, and sustainable development, health, well-being of the individual, and also the society as a whole. And all these are very complex problems, but we physicists have the curiosity to understand this fundamental principle beyond all this complex problem and across different scales. And using, like we are going to hear today, advanced technology to collect data and analyze complex data. And nowadays also using AI and advanced machine learning technology. And I think importantly, we physicists build a physical model and to understand the principle beyond all these complex properties, right? And in physics department, I spent a few words about physics department. So our teaching program and research center around these opportunities offered by the grant challenges. As we see, scientific research and technology innovation is the key to seek solutions to tackle strong scientific problems as well as the societal challenges. So our research focuses on two niche areas for those colleagues online and here to understand that our department. One is material science, advanced material, and especially focusing on interdisciplinary application to energy, health. And the other one, niche area is our physics complex system. And we know last year the Nobel Prize in physics was awarded to complex system. Yeah, we use physics approaches, data connection, analysis, and modeling, and cover the topic of like statistical physics, brain study, human microbiome, cancer, and also even traditional Chinese medicine. Yeah, the department is very actively recruiting excellent young scholars to join us to strengthen these topics. And the UG our UG and the master program focus on energy, green energy and smart technology, aiming to nurture young professionals with knowledge and technology to help with the sustainable development of our society. So I welcome those colleagues online to visit us and visit our website for these exciting events, and so you can come and visit us and talk about. So without further ado, I pass the time back to Professor.
Thank you very much. So hopefully, especially for those online, next time you could really come here and visit us, visit the department. Okay, so let me say a few words about today's distinguished speaker, Professor Yin-Zhe Ma. He's a full professor at the University of KwaZulu-Natal, South Africa, which is really far away from Hong Kong, and I had the fortune to visit that beautiful country just a couple of months ago. It's really nice. So he is a newly elected member of the Academy of Science of South Africa, really a young star in the field of observational and theoretical cosmology. So Professor Yin-Zhe Ma obtained his bachelor's degree in physics from Nanjing University and master's degree from the Institute of Theoretical Physics at the Chinese Academy of Sciences, and PhD degree in astronomy from the University of Cambridge. And he conducted CITA National Fellowship at the University of British Columbia, Canada, and a research associate at the University of Manchester. He then moved to the University of where he is currently in South Africa, from senior lecturer and up to a full professor. And he is involved with many research collaborations in the field of observational cosmology. And he himself chairs the NAOC UKZN Computational Astrophysics Center, and also has collaborations with Chinese colleagues. In particular, is adjunct professor at the Zijingshan Tianwen from 2017 to 2021. Maybe with a little bit of break in the past 2 years due to the COVID. So his research focuses on observational theoretical cosmology, which is really an exciting field, and more exciting now than ever. And the aim is to understand the fundamental laws of the universe and uncover the nature of dark energy and dark matter, which has been described as two clouds in the ultimate theory of the physics of the universe. And he is involved, as I said, many international collaborations, especially on the data side. In particular, his so-called square kilometer array science working group. This facility is still in construction. So I'm not going to take more of his time. So let's welcome Professor.
Thank you very much, and thank you, Chair, for your kind introduction, and thank you, Professor Tang, for the very nice invitation to this very famous university. And can the back hear me well? Can you hear me well? Yeah. Okay. Good. So yeah, today I'm talking about cosmology. I think our human Homo sapiens as a species on this planet, 17,000 years ago, when we walked out of the entire Africa, we experienced something called cognitive revolution. So our ancestors may not realize that one day we can split the atoms, walk on the moon, and write history books. But they have never could be anticipated that one day we are sharing some common culture with all intelligent species in the entire universe, which is cosmology. Because if we have one day communicated with any aliens, the intellectual species elsewhere, and ask them, what do you know about the history of the universe? They will also trace back to the same Big Bang, 13.7 billion years ago. So today I want to tell you a brief story of what happened in that 13.7 billion years. Because we have only less than 60 minutes, I count each second of my talk corresponding to 4.5 million years. So that's a challenging job. And bear with me if I'm not doing that well. Okay. So I think the entire history coming from Albert Einstein. This is Einstein from his famous theory of general relativity. And this is the equation, something called Einstein field equation, where the left-hand side is the geometric term showing how the universe is curved, how the space and time is curved. And right-hand side is something called matter-energy tensor, which is really showing you the matter itself, energy itself in the universe. So in John Wheeler's language, that the matter tell how the space curve, and basically the space and space-time tell how the matter moves. Basically, that's an interplay between the two. And initially, Einstein thought that this universe and the entire universe is static, because that's the most beautiful solution of this whole scenario, etc. Mostly physical intuitive. But unfortunately, the observer Edwin Hubble in 1929 discovered that the distant galaxies, which he used the Cepheid as one of the tracers, is actually moving away from us. So here is the velocity, here is the distance. The higher the distance is, the higher the velocity is. He just draw a straight line over here, showing that the further away the galaxy is, the higher velocity that is moving away from us, which means the whole universe is actually expanding. That's what he obtained. And basically, Edwin Hubble was a law student. You can see with such a complicated scatter plot, he just draw a straight line. But actually, the nature loves something very simple. So if one day you have some complicated diagram or graph and you don't know how to interpret it, just give me a pencil and I will draw a line for you for that. That's probably the solution for it. Okay, so because the universe is actually expanding, and when we trace back to the beginning, it's definitely not the miniature of the current universe, because at a very early time, it must be hot and very dense. So there must be some evolutionary scenario from the very simple beginning all the way up to now, the complicated cosmos. So therefore, the wrong picture is the Big Bang. The wrong picture of the Big Bang is some explosive scenario. People always ask me, what really bang? Where is the bang? Actually, there is no bang. This is the wrong picture, but the correct picture should be the evolutionary scenario, where currently there are some distance among galaxies, but at early time, it must be coming from some very hot and very dense plasma. That is where it really comes from. So really, what the entire Big Bang theory talks about is all about the aftermath of the Big Bang. There is no theory about the beginning. There is no. And don't trust any theory tell you anything before that. That's all metaphysics, basically. It's all about the aftermath of the Big Bang. So today I'm going to basically talk about this entire evolution of 13.7 billion years, from all the way from radiation dominant era to matter and to the dark energy dominant era. For the time being, I want to pick up a few very important epoch: inflation, Big Bang nuclear synthesis, recombination, reionization, and talk about in-depth, about what physics that it indicate and what new things we can learn. Okay, the first thing I talk about is Big Bang nuclear synthesis, because that's the first observational pillar of this whole Big Bang scenario. So to understand this, we must understand that, I will talk about this diagram in a minute. I think everyone knows this diagram. So one of the major theoretical, okay, I'm going to, I see, okay, thank you, yeah. One of the major observational evidence for this Big Bang scenario is that the helium particle, which is the nucleus with number 2 protons, is actually occupying 24% of this atom, 4.6% of the entire universe. And this is actually one of the major observational pillars to support the hot Big Bang, because this is a theory from George Gamow, the very, very famous Soviet Union physicist, and then basically went to the United States in his late age. So what he said is that if the universe was very hot at the beginning, for the first 3 minutes, it must synthesize through this very simple nuclear physics network an appreciable amount of helium. And so, I mean, if you observe a large amount of helium over here, it indicates that universe must reach some temperature 10 to the 10 Kelvin. So if you observe a lot of helium, must indicate that temperature, because the binding energy of deuterium, which is this element, deuterium, which is isotope of hydrogen, is 10 to the 10 Kelvin. So you can see this network that deuterium is some unescapable step to synthesize helium, right? So therefore, if you observe a lot of helium, the universe must reach the temperature 10 to the 10 Kelvin before. So that's really the first evidence to indicate the universe must coming from a temperature at least 10 to the 10 Kelvin above. And in fact, the center of the star, because the center of the star is only about 10 to the 7 Kelvin, the star can only produce no more than 2% of helium, right? So therefore, if you have 24% helium, it can't really synthesize from the star. It must coming from something even something significant. So that is a prediction, very significant prediction by George Gamow by then. So now let's see what is the current status of this whole thing. What is the current observation evidence? The major evidence coming from something called Lime alpha forest from the modern telescope. So let me play that again. So if there's a background quasar, which is really some very luminous object at distant universe, and the quasar will emit some intensity of the spectrum as a function of wavelengths, right? And the major significant peak is this Lime alpha emission. Lime alpha means the transition between principal number equals 2 to number equal 1. That is a major emission. And as the light passing through all the intergalactic medium to us, then the wavelength of light is being stretched out because of the cosmic expansion. So the whole spectrum is shifting to the right-hand side, to the longer wavelength side. But if there is some gas cloud in between, and that gas cloud will produce some absorption trough like this, and it will absorb some of the light, and you can basically identify some of the very metal poor gas cloud which represent the primordial component of the nuclear synthesis, and measure the absorption trough and derive the deuterium abundance. So this is the current the most precise measurement, and this is the simulation done colloquium I, and you can see this is the most up-to-date result. So this is the Cook et al., and that is the current measurement of the deuterium abundance. And you can see that is the measurement of the y horizontal axis, and this line is the theoretical predictions from the standard nuclear physics calculation. And the thickness of the line, you see there's a finite width of the line, is due to the uncertainty of the cosmological parameters, right? So it allows some uncertainties. But if you see the line intersected with the omega baryon density measured by the CMB measurement, it gives you a value like this, which is exactly equals to the deuterium abundance that measured from the Lime alpha forest. So the two different experiments are actually consistent with each other. So the CMB measurement of the baryon density intersected with the theoretical prediction give you a value of deuterium, which is exactly the same as measure from Lime alpha, completely different experiment. It means that this model really works, right? So therefore, this is the entire picture. So the chemist periodic table of elements, this is all you have learned in your high school chemistry class, right? But if I see the same thing in the eye of astronomer, I see something different. This is the astronomer's point of view of the elements. So hydrogen and helium are actually, most of them are actually synthesized from Big Bang fusion, whereas the others are coming from the post-astrophysical processes, right? And you have some heavy element in your body, and you are basically, in a less romantic way, the nuclear ash, nuclear waste of these post-astrophysical processes. If some of the lady may have get married and get some wedding band, some gold ring. If I ask you, where does your gold ring come from? The physical answer should be gold is coming from merging of the two neutron stars. That should be the correct answer you gave to me. Okay, so this is the astronomer's periodical table of elements. And if I see the same thing in a cosmologist's point of view, then the table, then this whole thing can also be changed. This is a cosmologist's periodical table of elements, where in the entire universe sense, the area is called, basically we make the whole thing area proportional to the cosmic abundance. The hydrogen take about 74%, and helium take about 24%. And all the rest, adding together all the rest, is less than 2%. Right? So in cosmology sense, only hydrogen and helium matter, the other thing doesn't really matter. That's what I want to say. And the amazing aspect is that this table has not yet been changed since the universe was 3 minutes. So from 3 minutes all the way up to now, 13.7 billion years, this thing doesn't change by more than 1%. How amazing that is. Right? This whole thing has been fixed when the universe was only 3 minutes. Right? So I think this is how wonderful that this theory of Big Bang theory is, and the current development and the current measurement is. Okay, so that is the first story, which is the first pillar of the Big Bang theory. And what was the second? The recombination. That is the major thing, bring our human being into the era of precision cosmology. We can really do something in a very precise sense. So this whole recombination really comes from very simple physics. So this is the 4 different components of the stuff in the universe. The dark matter, of course, non-interactive, something we don't know, only provide gravity, and gas and photon and neutrino, of course, right? You can see that as the universe evolved, when at very early time, because the universe was very hot, the gas and photon are mixed together. The red dashed line is mixed with the blue solid line here at a very early time. Okay, let's replay that again. It should be replayed. Okay, so it's mixed at the hot plasma and propagate at the speed of sound because there's some random fluctuation in the universe. And however, at the time of 380,000 years, these two separated because the universe becomes so big that the interaction between gas and photon become less and less. Eventually, they don't interact. It's just like here, for instance, we are having a busy party and everyone bumps into each other. Of course, we have frequent interaction. But think about the size of the room become bigger, 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 bigger. And then until it's large, so large that in your lifetime, you will not bump into anyone else. Then you decoupled from the rest of the hot plasma. And this is the whole thing. So as you can see, after 300,000 years, the photon will just free stream as the redness particle we call the cosmic microwave background radiation, which I will show you in a moment. And then the gas will just travel to a distance about 150 megaparsec and forming a small gravity potential well, and then it will attract dark matter falling into it, and therefore forming the galaxy and so on. So this is the acoustic wave. The sound wave propagates at the early universe since the Big Bang all the way up to 380,000 years. And you can see that this acoustic wave is propagating to a certain finite distance of roughly 150 megaparsec. However, in the real universe, there's a lot of such random random fluctuations, random initial conditions. What you see is some blurred, pretty much random structures. Okay, this is just like here in the water pond. You drop a stone, and the stone will make the wave. It will make the circle, hot wing, cold wing, hot wing, cold wing, like crescent top. However, in the universe, you have a lot of these random fluctuations. So what you really see is some patch which is hotter, some patch which is colder. That is a blur structure, pretty much, right? And this is part of the structure you can see in the cosmic microwave background radiation observed by the modern satellites like WMAP and Planck. So this itself is fluctuation at 380,000 years since the Big Bang. So the whole thing is the universe by then. Very impressive. And now you can see the hot spot like this and cold spot. And universe here is really like universe here. There's not much difference. I mean, there's some difference in details, but in terms of structure, they are pretty much the same. Now the question is, can you reconstruct the repo? Can you reconstruct that repo which I just showed you in the video? If the story I told you is correct, can you verify it? So the answer is yes, you can. So if you basically for each of the hotspots, you cut a little patch of a few degrees, covering the coherent length of the sound wave, acoustic wave, and you stack them together, you add them together, right? And you basically by stacking a lot of them, you actually wash out the random phase, and you see something like this. So around each of the hot spot, there's a cold ring. Around each of the cold spot, there's a hot ring. The same for WMAP, the NASA satellite, and Planck, the ESA satellite. Coherent structure you see in both. You can really do this very easily. I mean, you can download these maps. These maps are all publicly available. You download it once your programming skill is good. You do it 2 hours. You see the most important structure at early universe. You don't need to do any complicated analysis like a Fourier transformation. You don't need to do that. Just some real space cut off, added together. You see this. This is the most important effect happening when the universe starts all the way up to 380,000 years. How impressive that is. I always give this to my students as a first practice to do computer programming if they want to do a project with me. And they do see the most impressive structure that one can see in the universe. Okay, you can also see that on this map, there are coherent structure on all different scales. On very large scale, as I said, the universe here doesn't look so much different like there. They're pretty much the same, right? And also you see fluctuation on small scale as well. So basically, from 1980s, astrophysicists started to this whole endeavors try to measure all of the fluctuations on different scales and try to use that to measure the content of the universe, try to use that to determine what's really going on in the universe, and also about the inflation model and so on. So I'm going to show you, if you're just looking at your screen, I'm going to show you this journey for the last 40 years. If you're just staring at the screen and no change, right? So basically you will see that in 1980s, the data was so poor that it was unable to constrain the underlying theory. This was underlying theory, and this was the data by then. Of course, the error bar was so big that it can't really tell you anything about the underlying theory. But if you looking at my screen, I'm going to show you what happened in the last 40 years, right? You will see the error bar become smaller, and the noise become lower. The angular beam, the angular resolution become better, become smaller. So therefore, the higher multiple moment, which is corresponding to a smaller angular scales, can be measured, and also the instruments are better calibrated, and sky coverage become larger. Okay, just look at it. 1990s, it's like this. This is the famous NASA's COBE satellite, measuring the degree scale fluctuation on the sky. 1994 to 1996 was like this, and then 1997 the first peak is measured. 2000 the first peak is measured. 10 second is also measured, and 2001 the first peak, second peak all measured. 2004 this and this without any curve. You can see a peak, and maybe the third peak. All right, 2006 a few acoustic wave was measured, and by then 2006 the cosmic string, the cosmological defect generated from the cosmic predicted by string theory was basically ruled out. This one cannot produce you a coherent fluctuation, a coherent cosmic seed that come into the horizon after the inflation. So it has been ruled out by then. And then 2008, it was like this. And then I started to do my PhD. As what Professor Tang had mentioned, I did my PhD in Cambridge. I catch up a right time to enter the field, because in 2009, the Planck was launched in May in French Guiana in Latin America. And I remember I watched the launch event, and this was me. I was punting in Cam River. And this was my, after a few years, this was my graduation day with Lord Martin Rees, the famous astronomer, the Astronomer Royal in the UK. And by then, this was the background was Trinity College, which is a very well-known scientific college in Cambridge. And you see the same structure as what Isaac Newton saw 400 years ago. Nothing have changed, and externally, nothing changed. Internally, of course, it changed. It's a nice place. So I started to play this Planck data for my PhD and also for my postdoc. You can see that this was just before Planck data was released. You can see the NASA's WMAP satellite combined with ACT, combined with SPT, and showing you a coherent measurement of the spectrum all the way from the small L, the large angular scale, all the way up to large L. But then Planck come out 2013, 2014, and now this this is the pretty much the ending result for that almost 40 years journey. You can see that the data is here and is really exquisite measurement of the whole spectrum, right? And the data you see over here, the error bar is just so small to see it visibly. And the blue curve is a model of the lambda CDM, the cosmological constant lambda, which is Einstein's additional term in the field equation, plus the cold down measure. It's really going through the prediction, really going through all the data magically, isn't it? And you can see the residual. This is the data minus theory, showing pretty much consistent with zero, And there may be some little systematic over here, but it's pretty much very well consistent with each other. Okay, and so this is a major trend of the modern cosmology, which is trying to measure the cosmic microwave background radiation and use that to constrain cosmological parameters. Okay, I'm going to show you in a moment. So what I want to show you is that this whole spectrum is very sensitive to different kind of physics at early and late times. And this is pretty much half of my whole career is about. So for instance, for the very large angular scale, you have large scale anisotropy, which tell you some super horizon mode of fluctuations. And over here, this part is about inflation, which is also on very large scale, accelerating expanding at early time. And this is about dark energy because the first acoustic peak indicating the distance from the larger scanning surface to us, so indicating how fast the universe expands and therefore how much vacuum energy there is. And this is about baryon acoustic oscillation. It's about the plasma effect, which I mentioned. And this is about reionization because after reionization, there are more free electrons in the universe, which will attenuate the light propagating from the larger scanning surface to us, therefore produce a depression. And on very small scale, there will be a secondary order anisotropy effect, things like a Sanyaev-Zodov effect. Okay, these are details, but what I mean is that this whole spectrum is very sensitive to different type of physics on large scale fluctuation at the early universe, like inflation, and also about the small scale anisotropy due to the secondary effect, due to the galaxy cluster and etc., which is local universe effect. So really, 30 years ago, we were here. And 30 years later, we are now here. 30 years ago, we can only see error bar 200, 300 times larger than the underlying theory, whereas now the data becomes so exquisite that it can tell you a lot on the content of the universe and so on. Isn't this impressive, right? I mean, I think when I was a student at Nanjing University, which Professor Tang just introduced, I saw a professor give this talk. I said, wow, this is so exciting. This is for me. This part of science is for me. I'm going to study it for my master and PhD, and I have never left the field. I think it's just so exciting to work on it. Okay, and you can see that not only we're able to measure the temperature fluctuations, but also we can measure the polarization of the microwave background experiment. So this is the temperature and polarization cross correlation, the power spectrum, and this is the polarization, emo polarization, auto power spectrum. So, and you can see the data is also become more and more accurate. Now with the Planck, this data is really accurate apart from large L, which the error bar become bigger. But the blue line here is not the best measurement from the data. The blue line is a predicted lambda CDM model, and from the previous one, the TT power spectrum now predict what is the correlation here, what is the polarization here. And you can see the prediction going through all the data points perfectly, right? It's like if you know the TT, if you know the temperature auto power spectrum, you already know what's happening over polarization, right? It means high level consistency between different kind of measures. So it really works. And how did we extract the data from such a complicated experiment? So we have the telescope, the Planck satellite, and the satellite take time all the data and it basically pointing to one part of the sky for 30 minutes, integrated and use a gas propeller to tilt it, And then it will also tilted angle so that it will take half year, 6 months to survey the entire sky. So that is we take the time order data. And because at our detector side, we have several frequency channels. I mean, in Planck in particular, we have 9 frequency channels, all the way from 30 gigahertz all the way up to 800 megahertz. So we are able to measure 9 different maps from this time order data. So we do a map making, and then we do component separation, because for those maps, some of the map at low frequency is contaminated by synchrotron emission by our own galaxy. For high frequency map is contaminated by intergalactic dust. So we want to combine them somehow and try to subtract these contaminants and getting the most primordial signal out of it. So we do component separation and get the most clean map as possible. From this map, we can do likelihood analysis. We can calculate the power spectrum of the microwave background radiation, and then we can then this is we can compare that with theory. In our theory, we can put into a number of parameters, things like omega cold dark matter, the fraction of cold dark matter, the fraction of baryon, omega baryon, and tilde, etc. I will show you in the next slide. But these are the take-home cosmology parameters that you want to measure. And you can allow your parameter to vary, and therefore this curve is going to change on that diagram, and using Markov-Chain Monte Carlo to do the least square fitting for that data point. And eventually you will obtain the best fitting parameters of your interest. Or you can do some cross correlation with this with other observations, and therefore extract whatever your parameter of interest. Okay. So nobody will remember what this billions of data is. I mean, it's about data compression. From billions of data, you compress to a few million pixels. From a few million pixels, you compress to a few thousand numbers. Then eventually, you just take home with a few numbers. For instance, what is the neutrino mass? That is a very sexy number, right? Everyone wants to know what is the neutrino mass. So that is what you take home, right? That is what you think about every day. So, and also about alien universe, which I will show you here. So this is the most important parameters we can measure from this whole set of cosmological data. For instance, the tilt of the scalar perturbation is about 0.696, is deviated from unity, and Hubble constant H0, right? This is about how fast the universe expands. So it's in the unit of kilometer per second per megaparsec. It tells you at what scale the universe can expand at some certain speed. Right? And this is the fractional dark energy density, which is about 70%. This is about the fractional matter density, contain both the cold dark matter and the cold dark matter and the baryons, which is what you see. And this is the reionization redshift, which is about 8, which tells you when the universe reionized due to the formed first star and galaxies, which emit a lot of ultraviolet radiation. I will show you in a moment, okay? And the very important parameter is the last one, the age of the universe. One of the most fundamental parameter one can measure from this. This tells you the current, experiment tells you it's about 13.8, 13.7, 13.8 gigayears, right? So this is a way to answer a philosophical question in the quantitative science, because if you think about the ancient philosopher, right, they might have also thought, what is the longest time of physical reality? This is the longest time with physical reality, and now we can measure this philosophical question in a quantitative way that we can even give error bar on it. How fantastic that is, right? So when I think about this, I feel such a passion of doing this kind of science. Okay, so let me just cover you one mystery. So this omega C is a fractional cold dark matter. Right? Do we know what is dark matter? No, we don't. In fact, it's a huge scale to search, a huge scale. So this is the mass of dark matter, which can really ranging from the axion-like particle, which is really like very wave-like feature, or axions, and all the way up to sterile neutrino, WIMP, the weakly interacting massive particle, or primordial black hole, which could be also formed from early time. And we have no idea whatsoever where that particle of dark matter is on this axis. We don't. And so this is what Jane people say. For dark matter, you don't know where to look. No, you don't. And you have to work very hard to look for everywhere as possible, right? So this is his Nobel technical interview of Jane people in October 21, 2019, which I find is the most impressive comment on this. You don't know where to look, so you have to look for everywhere as possible. And okay, so let me tell you something interesting which we can derive from the measurements. So one of the very hot topic in physics about neutrino, right? What is the neutrino properties and what is their hierarchical structure? So these are the outstanding issue. Whether it's what is the absolute mass scale, what is the mass ordering, and what is this Dirac or Majorana neutrino, or whether there's additional neutrino or relativistic species. So currently, from the solar and atmospheric neutrino oscillation experiment, we know there's a mass square difference between mass eigenstate of neutrino, right? So from there, you can organize the square mass difference in two ways. One is a normal hierarchy where the two low mass eigenstate is below, and one is up. So this will give you a lower mass. So sigma m nu must be larger than 58 milli electrovolt, 0.058 electrovolt. Whereas here, this will give you an inverted hierarchy, which the sum of this will be larger than 0.1 electrovolt, basically. But cosmology can answer this. Cosmology can measure the total mass of neutrino, and therefore it's possible to pinning down the structure of this and this, which is hardly to achieve by the particle measurement itself. And the reason is because if we can measure the microwave background experiment very precisely, then the neutrino is will sensitive to this lensing, gravitational lensing, because neutrino will move, basically smooth out a lot of structure, and therefore there will be less lensing over here. And more neutrino will make the radiation to matter transition time to be a little bit later, so that will change the early integrated Sartre-Wolff effect. And more neutrino will also change the late time integrated Sartre-Wolff effect because it will make the gravitational potential to decay. So if you have an exquisite measurement on this spectrum, then you can convert that, you can use that to measure neutrino mass, okay? And this is what we have. Right? This is combine the cosmic microwave background temperature and polarization measurements with other cosmological measurements. You can see this is the current upper limit. Sigma m nu is less than 0.12 electrovolt. This is what cosmology tells you about the neutrino mass. And you can see the current joint constraint is actually pushing the whole contour towards left. Whereas this gray area, I don't know, people can see it now. Okay. This gray area is prohibited because it has to be, the whole thing has to be above 58 milli electrovolt. So this part is prohibited. And this is a normal hierarchy, this is inverted hierarchy, and actually the current data seem to prefer normal hierarchy. But future data will compress it better and to make possibly the detection. Okay, and also neutrino cosmology can also tell you a lot about particle physics as well. For instance, for this diagram, this is our current standard model of elementary particles, with these quarks, with leptons, and with gauge bosons and mesons, and also the scalar force carrier. So we know this, but if there's any particle which is not discovered in this table, and that particle may once a while was in the hot bath of the universe at a very early time, it will leave some imprint. The way that it leaves imprint is through this ineffective, the effective number of relativistic degree of freedom. The current standard model is 3.046. Why it is not 3? Why it is not 3 generation of equals 3 exactly as a number of neutrinos? There's some detailed reason I will explain to you later. But anyway, just to assume this value, if there's any particles like this, and once a while in the hot plasma at very early time, and may decouple at very early time, it will contribute to a different value of ineffective. It will increase that ineffective. It will increase that effective degree of freedom, relativistic degree of freedom at early time, which if you measure that precisely, it will, you have the possibility to detect some unknown particles. not in this table. It's possible. And in fact, this is what is one of the major scientific objectives of the CMB stateful experiment currently being planned and will be built in the US. And I'm also part of the team. So it will be it will have 500,000 detectors in Antarctica and in Chile, and trying to measure the CMB power spectrum, the polarization spectrum on the very large, very small angular scales, which is trying to do that precisely. All right, let's see the time. Okay, so I should close soon. And the last important epoch is about reionization, which I would like to quickly show you. And this is about the reionized process at about 1 billion years after the Big Bang. So you see this little place where the first stars and galaxy was formed, right? And it will emit a lot of ultraviolet radiation, and that radiation will reionize the neutral hydrogen being formed at early on, and gradually expand the reionized region and gradually eat out all the remaining neutral region. So, and then gradually universe become more and more reionized. And this is a magic video, isn't it? And if you staring at it, you will see the ionized region become ionized bubble become larger and larger and larger. Eventually, the whole universe become ionized. This is a magic video to watch, but it's real. Yeah. Okay. So in fact, this is a major thing in cosmic dawn and reionization. So is a major thing that in South Africa we're doing the square kilometer array, which Professor has noticed that while he was visiting, and this is basically the major science goal to measure the universe transition from dark ages all the way up to ionized universe. And I would like to quickly jump. So this is also the reason. This is also the motivation to do JWST, because previously for the Hubble Space Telescope, there was one of the major scientific breakthrough is that Hubble used 2 weeks, around 2 weeks time, the director's discretionary time, to look at one patch of sky, which is only a few arc-minutes. For that patch of sky, it was previously no known source in that patch of sky. It's all dark. There was no catalog source in that patch of sky. Let's see whether there is something in it. In fact, after 2 weeks of integration, they saw a lot of things. This is something called Hubble Deep Field. They see a lot of little smudges. Each smudge, each little dot is actually an entire galaxy. The reason we don't see them in our normal telescope is because they are too faint. They are just too far away to be measured. But with a Hubble Space Telescope integrated by 2 weeks, it was able to pick it up. Right? And now for JWST, the James Webb Space Telescope, which was launched late of last year, is going to have 5 to 6 more collecting area. Is going to be able to measure 100 times fainter objects. Those fainter objects are actually at much larger distance formed much early on. And it will possibly reach redshift 20, which is about the transition time from neutral to ionized. And in South Africa, we are using a different technique called hydrogen intensity mapping. So this is the neutral hydrogen at ground state. Basically, we are looking at neutral hydrogen at ground state, where this transition between we call hyperfine splitting, between the state where the electron and proton spin parallel to anti-parallel, and it will emit some radiation with the wavelength 21 centimeter, right? So this is a really long wavelength compared to the Lambda alpha, because the energy gap is so small, it's very small, right? And we'll basically be able to measure neutral hydrogen with this wavelength. So what you observe on our telescope is the reference wavelength 21 centimeter times a factor of 1 plus z, where this is the cosmic expansion effect. So if you measure a structure at redshift 9, for instance, okay, 9 plus 1 is 10. 10 times 21 centimeter is 2.1 meter. 2.1 meter is quite large, right? Quite long. The wavelength is like this. So you need a meter-sized dish to pick it up. Otherwise, you will only observe the background signal. So this is the motivation that we do this science. So I'm part of this team, the Hydrogen Epoch Reionization Array, HERA, H-E-R-A, which is a joint collaboration between South Africa and US and UK to build these 14-meter dishes in the Karoo Desert to measure that signal. So this is a real picture of the dish array in Karoo Desert in Northern Cape. So from Cape Town, you drive 7 hours, you can reach there, or take a small flight, 1 hour, you reach there. And this is a more technical parameter. This is the real photo of the Hira, and this is what we measured. So these two data points pointing downward are the upper limit we published last year, and this is the power spectrum of the 21 centimeter as a function of the redshift. And you can see this is the underlying fiducial model of the transition between of the realization between neutral to ionized. You can see the current data is still 200 times larger than the underlying signal that we can anticipate it. But in the next few years, our target, our aim is to press that error bar down, to better calibrate data, to press that down, to make that first detection. It's going to be a very exciting journey, a hard-working and very exciting journey. So compared to the CMB measurement, which I just showed you, 3 decades ago, we were here. The data was so large that people cannot anticipate that one day we will reach this accuracy. Now we are in the same journey. If you look at this error bar, it's also 200 or 300 times larger than the theory. But I hope it won't take 30 years. Otherwise I'm too old to win this. I hope in the next 5 to 10 years, we're going to be able to bring this data down to make some first detection, and then gradually improve it to see, we can use that to understand a lot of cosmology. So what really happening over there. All right, so in the next few years, these are the future CMB survey. A few collaborations in Antarctica, in South Pole, in Antarctica, sorry, in Atacama, and this is in China, Tibet, and this is the Lightbird experiment in the space. And in the future, we also have DAISY experiment in the US, the optical telescope, and also LSST. This is the large, or we can call Verda C. Rubin observatory, the large synoptic space telescope. And also, in the future cosmology survey, we have Meerkat telescope, the precursor of SKA in the Karoo Desert of South Africa. We have Hira telescope. We have HiRISE telescope also in South Africa. And this is a famous China's FAST telescope, the 500-meter single dish telescope in the Guizhou province. Right? All of this is going to measure the neutral hydrogen in the early universe, in the large scale of the universe. And finally, I would just use last 5 minutes to discuss one question, and then we close off. I have mentioned so many observables, so many observational experiment, observatories going to measure the universe, etc. And is the information infinity? Is there infinite number of modes that you can measure in the universe? Well, you will see that it's not infinite. Actually, there is a finite number of modes you can measure about the entire universe. Okay. So this is the maximum physical reality. So this is maximum physical reality. We are here. We are looking at the distant universe. So the maximum speed that the light can travel is c, which is maximum speed any signal can travel is c, the speed of light. Right? There's nothing can faster than c. And the longest time is the age of the universe, which is the number which I have just mentioned. So c times th is roughly the distance scale, and that is the maximum physical reality, which is about that you multiply by some GR correction, all the one terms, basically. So there's a finite space that a signal can travel. Outside that space, you just don't know what happened, right? So a few years later, earlier, we wrote a paper. I wrote a paper with Douglas Scott on how much cosmological information can be measured. Here, what I mean is that we only count those modes which are still linear on the large scale and can be still used to trace back all the way to the beginning, and therefore understand a lot of Big Bang information. So that mode, if we count it correctly, is not infinity. It's a huge number, but not an infinite number. It's about 10 to the 12th number of modes. So in principle, any sort of cosmological parameters you can measure have a finite signal-noise ratio. That is 10 to the 6. It's a huge number, but it's not infinite, right? And in fact, what happened on Earth, what happened on your scale, or actually in our whole solar system, actually in our own galaxy, doesn't really matter to the entire universe. For instance, you are wearing a black shirt, and does that information tell you anything about the whole universe? No, it doesn't, right? You are too small. In fact, our whole galaxy doesn't really matter, right? So there's only certain number of modes we can measure in the universe, and this is the conclusion of this paper. Okay, so now if we, so all we do is really looking at the pulse light cone, all the way up to the cosmic microwave background radiation time, and to see the whole universe by then. So now if you imagine, what if I'm flying away? What if I'm just going to that light cone? What if I'm flying away from our Earth all the way up to the Big Bang early time? What should I see? And now you see the screen. This is what you see. This is a WMAP satellite. It's on the second Lagrange point of the Earth and Sun system, and you see different planets. This is Saturn, the Saturn ring, and now we are flying out of our own solar system. Then we gradually see the interstellar space, right? Then we see we are in a spiral arm of the Milky Way, halfway to the center of bulge of all stars. And then once we fly out of our Milky Way, we see our nearest galaxy, which is Andromeda, 700 kiloparsec away from us. This is Andromeda. And then as we fly away from these local groups, we see more and more galaxies, and we fly away, we see galaxies younger, and then we go into dark ages. Before dark ages, it was the hot plasma. This is a hot plasma, all the way traced back to the beginning that we can see. Right, so, right, isn't this? This whole video really summarized the entire 13.7 billion years in just 20 seconds. So what we will never know, we could be in this four dimensions kind of space and time, whereas it could be fifth dimension, which we never know. That could be just a small distance away from us, but in a higher dimension. Or we might be in part of the universe that the entire space-time has this disconnected bubble between, and this is something called eternal inflation scenario. And then apart from this pulse light cone, apart from the observable size, there's nothing else we can know. So what we will never know, the maximum physical reality is C times T age of the universe. That's corresponding to the limit of science and humanity. Thank you very much.
Well, thank you for this very excellent talk and explanation. So nicely, the wonderful science that took place in the past 30 years behind what we read in the newspapers, the report for the journal. I'm sure there will be many questions, and probably also questions from the online audience. So let's start with questions by people who are in the room. Any questions?
I'm not going to do that. You said you are going to build this new system to measure data 80, maybe 20 or 10 years before to then come again to the theoretical curve that the data can be consistent with theoretical prediction. If that is true, and then you already showed that the other data after 40 years really become so consistent with theory. This means the theory is correct, then why we need to measure everything we can predict from this?
Yeah, that's a good question. So basically, we don't know what is theory about. Basically, for 30 or 40 years ago, we saw the error bar was so big and there was some curve, but that curve has a lot of uncertainty. 30 or 40 years ago, we didn't know there is a dark energy exists in the universe. By then, we have some simple idea that universe may be just full of matter itself. So as the data become more and more accurate, then it stimulates theories to think about carefully, what could be the theory of it. And therefore, when the data become precise enough, then people can fit different models and to see, which model can fit my data best and predict my data best. So it's an interplay between data and theory. So that's also the charming aspect of the field, which is this great interplay between data and theory. So once the data improves, the theory will that can tell me about what could be the real theory. I mean, which theory really better fit the model, and that also stimulate the theory to think about what could be the other explanation.
Maybe I can follow up on this. So if imagine your curve, you after many years you think the technology is so good, but it still didn't fit to the data. So what you think is because the technology is not enough, or whether you now start to think about that you need a new theory?
That's a very interesting question. Actually, we are facing such challenge almost every day. There are also some discrepancy like the H0 value, the Hubble tension, etc. Also, so first of all, there are different schools of thought. Sometimes we look at if we are less confident about the measurement, then we look at the measurement. We have to make sure most of the time we have to make sure the measurement is correct. But sometimes if the measurement has been double checked and being complementarily checked by other experiments and make sure that is correct, then we need to look at for the new theory. So it's really also interplay between this. And I have to tell you that as a person working in this field for theorists, we find that the theory which a theorist invented, a theory would only be believed by a theorist himself, not by others. Whereas for experimentalists, he is the person who believes his measurement. He doesn't believe his measurement, where all other people believe his measurement. So that is an interesting aspect.
Thank you. Professor Yin.
Yes, a question online.
You mentioned the graph method. Perhaps I'd like to also comment on the dark energy, something like a negative gravity.
Yeah, that's a very strange thing. So what happened is that historically, thank you. Yeah. Historically, the lambda was invented by Einstein in early 1990s, in about 1990s, after he invented the Einstein field equation and so on. So he wanted to use that lambda to balance the gravity. So gravity would contract everything together, right? He needs some extra thing to balance out the gravity so that it will make the universe stable. But then when Edwin Hubble found the universe was actually expanding, then Einstein said, I better get rid of that lambda. It's the biggest blunder in my whole career. But actually, what he did is correct. So now we see not only the universe is expanding, but accelerating expanding. So we need to invoke that lambda again to explain this phenomena. But there is a huge problem between the measured value of lambda and the vacuum energy, which is the natural explanation of what lambda is. So the vacuum energy predicted by particle theory is make a value of lambda, if you just make a reasonable cutoff, is actually predicted value 120 times higher than the observed value of lambda. So previously people think, if the vacuum energy really produced such a high value of vacuum energy fluctuations, there must be some mechanism to cancel it out completely so that we see a zero lambda observed lambda effect, right? But what you really see is some small value. It's like some cancellation, which is not exact, but leaves some residual value 10 to the 120 times smaller than the predicted vacuum energy, which is a big puzzle here in physics. So cosmological constant problem is the biggest puzzle in physics. It's not some, a small modification or some small improvement that one can do to solve this. But what we can see, what we can do observationally is we can measure more and more data from microwave background radiation from Sloan Digital Sky Survey, and we can use the data to constrain theory and to see whether that lambda is evolving or not, right? If it's really a constant or maybe a function of time. So that's what we can measure.
Yeah, in the last remark, you mentioned that there's a limit of the size of the universe, and maybe there's hidden dimension or I don't know, that there's a figure with some connected bubble kind of things. So your idea is that the actual structure of that is beyond science, right? Is that what you mean?
So what I mean is that you have a finite size of the observable universe. So that size is finite, but the universe itself can be infinite. There could be, disconnected bubble of space and time, whereas it's just much beyond the Hubble radius, much beyond your particle horizon that you have no clue to measure it. So that's what I said.
So that you mean that observation cannot answer those kind of questions?
No.
In that sense, do we have any idea whether the universe as a four-dimensional space-time, whether it's compact or it's completely open?
Yeah. So basically, we currently build that curvature information into the Friedman equation. We can measure that basically through our current observable, and the universe is look like it's very flat, spatially flat. So it means that the universe is most likely to be infinite, and we only have a finite size to observe. And what else? What is the space beyond that is not reachable for now.
So it's likely to be flat.
Yeah, it is. It's very flat.
And I remember there's a slide about the dark matter.
Yeah.
Where you have a look, and there's a gap between axion and something.
Yes.
So can you show that slide?
Yeah. So that gap, yes, that gap was previously thought to be. Let me. Right.
And stellar neutrino.
Yeah, stellar neutrino. So that gap was previously thought to be around neutrino kind of matters, neutrino kind of particles, but it's being ruled out because it has a free streaming velocity that can wash out a lot of loss of structure. So if you get all of the dark matter to be neutrino, then you wouldn't see a lot of loss of structure, and therefore we can't be here. Our own galaxy can't be formed. So yeah,
It's wonderful. It's somewhere you have to look.
Yeah. It's wonderful that we already exclude this from this parameter space as a major dark matter component. I mean, yes, neutrino can exist in some small fraction as we analyze, yes, but it can't be the major dark matter component.
Thank you.
Yeah, no problem.
Okay.
So,
Just
a follow-up question about it. So, if you look at Wikipedia or in your slide, neutrino you only put up an upper bound for the energy in terms of the energy. So, my question is: does neutrino has a mass, or how can we understand neutrino? It's very mysterious.
Yes, it's very mysterious.
So can it be? I think you answered the question already. But can neutrino consider to be part of dark matter or dark energy, or what is?
No, it can't. Well, first of all, neutrino can't be dark energy. Dark energy is some, anti-gravity, which is a vacuum energy, which can propel the universe accelerate expanding. So neutrino can't do that. And it could be a very small fraction of dark matter, but it can't be the major dark matter, as I said, because it will wash out a lot of lots of structures, and therefore making the galaxy cannot form. So, and currently these are the outstanding questions about what is the neutrino mass hierarchy, whether it's normal hierarchy or inverted hierarchy, and cosmology can answer that because cosmology can measure the total mass of neutrino from the precise measurement of the micro-diagram experiment. Does that answer your question?
I think, maybe I cannot understand very well. Actually, I have been puzzled by what neutrino. I mean, neutrino has been around for a long time. People know it exists, but then no one is really willing to say more on like is it does it have mass, right? Neutrino does neutrino have a mass?
Yes, I mean there is a oscillation experiment told you that it must have some mass. So even though the floor can be zero, I mean because of the square mass difference, the total mass must be non-zero. That is from the oscillation experiment.
Right. Okay. Thank you.
Last one.
you said two things. So you said the dark matter, you don't know where to look at. From all the observable ones, not dark matter. Is that right? I mean,
Well, only what's the
the dark matter, you comment that you don't know where to search. You have to search everywhere. And then you also said that you imagine there may be another universe, but you cannot observe that. That's beyond our observation. So I just thought, well, these two can be just the same thing. The dark matter is another universe that, like attracting, for example, this bubble is like attracted by another bubble, like you have the expanding, and say if you have one universe and another universe next to each other, but this gravitation thing is still working, then would we expect kind of non-isotropic? You say universes come very uniform, but maybe there's a very small kind of heterogeneity indicating say another universe next to us.
Yeah. So there are two things. One is about the dark matter. One is about the anisotropy of the universe. First of all, dark matter cannot be the gravitational attraction of the other space and time, because dark matter is responsible for forming the small-scale structures like our own galaxy, which is really small. So it cannot be a total attraction from another side of the universe. Otherwise, it will not helping this kind of small-scale structure formation. And in terms of anisotropy, is very little. So when you look at the universe on that direction, conditions don't differ in 1 part of 100,000. So any gradient across the entire cosmos is very small indeed. So we can't really imagine that the universe just stops at where we can observe. That shouldn't be the boundary. It must be in further extent so that it will produce very little gradient across the entire sky.
Thank you for talk. I would like to ask, what's the most special experience to you for studying cosmology? Since for me it's so different from other disciplines that we are familiar with.
What made you study cosmology?
Yeah.
It's because
I mean, the most special experience.
most what's the experiment?
The most special experience.
Expensive experiment.
Studying experiment.
Studying experiment.
就是说你在研究宇宙学这个过程中有什么就是非常特别的经历？就是因为这个学科对我们来说，非常的特别。
Okay, well, what special experience I had in studying cosmology? I think that's the question. Special experience. Okay, so yeah, that's a good question. First of all, it's a fascinating subject. It's something so interesting that once I know it, I can't keep it. I think I have already planned my whole career to study it. Okay, it's a fascinating thing. I think the special experience I had is the interplay between the theory and the data. It's not just on the data, it's not just on the theory. If the whole subject is about the field equations Einstein played in the early 20th century and no data, this field has long gone, basically. So it won't be thrive as a major advances in physics. So it's because the interplay between the theory and data, as people build telescopes and observe more and more galaxies, building a telescope to observe the photons, etc., from the early universe, and it will improve the theories that we can propose. It will rule out some of the theories, go away. This theory, like for instance, the famous one is the steady-state universe. The steady-state universe, the universe just stay as it is. The matter is just emerge with some phenomena. Beautiful theory by Fred Hoyle, Cambridge leader in cosmology in 1950s and 60s, but has been ruled out firmly in 1965 when people discovered the microwave background radiation. So this interplay between the data and theory is one of the fascinating aspect of this whole subject itself, and it's still going on. And now you see we are going to measure the 21 centimeter emission from the epoch of organization is going to measure more galaxies through the other telescope. So we're going to improve our understanding of dark and dark energy. So the whole journey is still going on. So that's make me very excited about what I'm doing, very passionate about what I'm doing.
Another question.
Yes.
Do you believe aliens or?
We will come to you later. We will come to your question. Okay, there is some question online.
So yeah, there's a very enthusiastic online participant, K-Log, and he would like to ask the question
Yes.
by himself.
Please, let's see.
Yes, this is Carl. Yes, a former alumni at the Hong Kong BU Physics alumni. Yes, yes, I have posed 3 questions. Maybe thank you for Professor Ma's your very exciting talk.
Oh, thank you. Yeah.
Yeah, the first question is about. I think you talk about the scalar perturbation. The index is about almost close to 1. So I'd like to know whether there is a specific inflationary model makes such a scalar perturbation index, and also does the lambda CDM model, does it consistent with that specific inflationary model? Yeah, this is my first question.
Well, the first question is about what I showed, the scalar perturbation, the spectral index is about 0.96. And he asked whether there's any specific model. Give me that number. And this is actually a very professional question, I have to say. So in fact, this is what we're doing. We're using that value and the whole spectrum, actually including that value, etc., to measure different inflation models. And basically, currently, interestingly, there is no known inflation model that can fix that can make that prediction very precise. And because for every inflation model, you need to produce an inflation period we call number of epochs 50 to 60, means the universe must expand e to the factor 50 to 60 number of times at early universe. So if you consider that thing in and then the current potential for different particle potential, it doesn't really produce the value like that. I have a different slides, not including this in this talk, but I'm in some other talk to show you that. But it's really, this is one of the challenge. What really drives inflation? It's currently, previously we thought if there is a scalar field with potential half m squared phi squared, right? Quadratic potential, which is a pretty much standard potential in particle theory. It can produce something, like inflation. But now that model has been ruled out. This is again the interplay between data and theory. And now the model seems to prefer the data seem to prefer a potential v as a function of phi as phi to the power 0.5. How come? This is a very strange potential. You don't see such a potential in particle theory, etc., in any of these vacuum energy, whatever consideration is. So at the moment, that is one of the problems that we are facing. So what really drives inflation? So that is an outstanding question. I think in the next few years, hopefully when the CMB stage 4 experiment, etc., provide better measurement on the polarization, we're able to clean that down. Does that answer your question?
Oh, yes, good, very good. And my second question is, a few years back, the Nobel Prize was awarded for the supernovae type 1, which suggested that the universe is an open universe. Is that the reason concern about the correctness of using the supernova type 1 as a distant indicator?
Yeah, so again, this is a very professional question. So the supernova itself cannot determine whether it's open or flat or closed itself. I mean, you have to combine that supernovae measurement with other cosmology measurement, 2 or 3 data sets together, especially combined with other complementary data sets like the microwave background experiment, which I showed, or the galaxy binaural acoustic oscillation data, the strong zero sky survey, to jointly constrain your cosmological model. So if you join these 3 data sets together and fit your model, then you find universe is actually flat. So yeah, so that is my answer. Yeah.
Oh, okay, yes. You have a more recent update. And my last question is, there are some news saying the James Webb Space Telescope found the image suggested that the Big Bang model is wrong. What are the unusual things found? But I think it's still too early to make such claim.
Yeah, I agree with you. It's too early to make such claim. Yeah.
So what is the exactly unusual thing that the JWST found at the large?
I think we can discuss that question offline. So it's a bit complicated to discuss.
Okay. Yes. Yeah. Thank you very much. I enjoyed your talk very much.
Oh, thank you.
Yeah, thank you very much. One more question. Okay, that will be the second to the last one. Where is it? Oh, okay. So this is what is his name? Adam Chen, Adam Quick. Is it? Which one?
Yes.
Oh, okay. Please.
Adam Craig.
I had a couple questions, but the first one was, is the age the age of the universe given in this presentation the same across different for all observers, or like is it specific to the Earth's frame of reference, or is there some other standard?
Yeah. Okay. You mean if I change observables, whether that will lead something? No, it doesn't. This is just derived from the background evolution model of the universe. So it's just a simple projection of the expanding history of the universe. So no, it doesn't. No.
Okay, so like if I were standing on some other particle that was moving moving extremely fast, the universe as measured from the cosmic background radiation and these other, assuming I still had similar sort of observation tools to what physicists here on Earth are using, I'd still see the same age of the universe.
Yes, because your relative motion respect to the microwave background rest frame is actually a dipole effect that you can see in the microwave background. So when you do the microwave background analysis in Fourier space, you can remove your dipole effect and then use the rest of the higher order terms, which is unaffected by this largely, and then you can use that to measure your parameters. So it's not affected.
Okay, sure.
Did you see you have another question, or it's okay? All right.
I did actually, but I don't know. Are we okay for time here?
Maybe, yeah, just if you ask, if you can keep it short, then
Yeah,
it's okay.
It's, yeah, does cosmic inflation also imply the information content of the universe is increasing?
No, actually, it has been diluting. So there could be other particles generated in, during inflation or, whatever early universe is. In fact, my other colleagues have many of such theory. But as universe is expanding so fast that all of these particles has been basically diluted away, and you don't see any relics from it. So it means that because of inflation, we see less things in the universe. Inflation just make your money less worthwhile, basically.
Fair enough.
Great. Yeah,
Thank
you
you
very much, Adam, for your interesting questions.
Thank you. This has been very enlightening.
Yeah, good. So before we close, maybe Professor Ma, would you care to answer this layman's question? Are there aliens? Just briefly.
Good question. There is no solid evidence for any aliens, but I think there could be, because it's really hard to think that in such a big universe where just observable size would contain billions of galaxies, where each of the galaxies contain millions of stellar systems, and now we know around each star there could be 5 or 6 planets, and there could be among them 2 or 3 habitable planets in a suitable wind temperature between 0 to 40 degrees centigrade. So it's hard to think in such a large sample only us exist. But on the other hand, we don't know in what condition life can originate it, right? So your question is about biology plus astronomy question. So I can only answer the astronomy part, which is in such a big statistics, it's hard to think that we are the only one. But biologically, maybe that biology, they have a different view on this. Thank you.
Can I just allow me to follow up on this? Fascinating. I think you just talked about this like a neutron, fictional, and like a big universe, right? And this different scale. But we are in between actually in the universe. And this scale of like human, also the planet, just talk about like maybe in the universe, not just us, maybe everywhere, like alien planet. How this like human or alien, our activity would have an influence possibly to the universe. Like we can change our planet and things like that. But how we could impact on like if there are so many aliens everywhere, impact on say the universe kind of evolution.
Unfortunately, I have to say, I see no way we can impact such a large scale. But on my aspect, I can see we can share such a common culture with any possible intelligent species, possibly in the universe, and think about what common culture that we can have with another alien. If in some day we have some communication. Certainly, just one sentence we finish off. Okay. Certainly, humanities, literature, all of this we count, because even within the human being, by different languages and countries, we are different, right? What about biology? Can you guarantee the other aliens also pass on their genesis genes through DNA double helix? You can't, right? And what about agriculture? They may not eat bread, they may not eat rice, as all of the things, gluten, etc., as we consume, proteins, etc. But there are two things we must share. One thing is about mathematics. If they draw a triangle, this thing times its square and this thing times its square must be equal to this thing times its square, times itself. And also about the cosmology, about astronomy. If they observe our own galaxy, if their planet is also in our own galaxy, they must also see the center of our own galaxy is a supermassive black hole. If they trace back to the beginning of the whole universe, they must also see we are coming from 13.7 billion years hot Big Bang. So that is a common culture we can share.
Yeah, very last question.
I read the idea just a few weeks ago that our university actually is two dimensions, not three dimensions. The third dimension is actually the kind of illusion, and our world is kind of a projection of the two dimensions of just like a bubble, and actually we are locating on the surface, and the three dimensions of world is just like a projection, and this theory can explain the dark matter, but why can't we just cannot observe and it just work on our world? How do you judgment this idea?
Well, I learned something new, but that theory itself is an illusion. Yeah.
Great.
Okay, I see.
Yeah, thank you very much. We really had a very successful lecture and also a lot of discussion afterwards. I think every successful scientific expedition will leave open questions for the future. And I think some of the questions being asked will be intensively explored in the future. And it's just the nature of human beings to try to understand our position in the universe, our relation with the environment. And I think there's a lot still to be learned in that respect. So Professor Ma, thank you so much for this wonderful lecture, and very informative, and we are very grateful to you. Thank you.
Thank you.
Thank you to all the outside and online participants of the lecture. Thank you. So
Thank you for joining online. Thank you.